So this is chapter 14. I'm going to work a couple of the integrated rate law problems. And when you are working on these, you should have your formula sheet out so that you have those right in front of you as you do them. So how these are going to look different is the fact that in these problems, they're going to tell you what order you have. So you're not going to have to determine that. That's a rate law. That's a differential rate law. So this one, decomposition of N2O5 into 2NO2 and 1/2 O2 in a carbon tetrachloride solvent is a first order reaction, okay, with a rate constant of 6.2 times 10 to the -4th inverse minutes. So this is your K, that's your lowercase k, at a certain temperature. So how can you look at that K and know that it's a first order? Now I know they told you that, but this is trying to help you out for future endeavors. So realize a zero order reaction would always be, K would be molarity over the time frame, okay, if it was a zero order reaction. If it was a second order reaction, the K would be 1 over molarity minutes, because again, what you would see is molarity squared, brought it over to the other side, you'd have molarity on the bottom. So if you have any problems where K is given, you could look at the units to determine if it's zero, first, or second order. Okay, so what is the half-life? So use your formula sheet. So half-life is going to be 0.693 over K. So that's going to be 0.693 over 6.2 times 10 to the -4th inverse minutes. So your unit is going to be, of course, in minutes for this particular one. So you get about 1100 minutes for your half-life. Okay. All right. Second part is actually the more interesting part. At what time, or what time is required for 20% of the N2O5 to decompose? Okay. So again, we know it's first order, so we could use the equation for first order, but we need to kind of figure out how we're going to know the concentration. So I know my initial concentration of N2O5, we can make that equal to X. So the initial concentration of my reactant. And then my final concentration of my reactant can be 0.8 times X, because 20% of it is gone. So that means 0.8 is still there. So I could take the natural log of 0.8X, which is my final concentration, minus the natural log of X, which is my initial concentration, is equal to negative K, which is 6.2 times the -4th inverse minutes, times my time. Okay, so do you remember your logs? If you subtract logs, it's going to be 0.8x over x. So you're dividing the two. So x is canceled. So you're taking the natural log of 0.8 is equal to negative 6.2 times the -4th inverse minutes times time. Okay. So try this in your calculator. The time you should get is about 360 minutes. All right, so see if you can do the next problem. Okay, number 2. Compound decomposes according to second order. So you want to use the second order equations. When the initial concentration is 0.1, the concentration falls to 0.075 in 2.5 hours. Find the K, and then see if you have the initial concentration is 0.5, what would be the concentration after 5 hours? I will come back on and show you the. So because it told you it was a second order reaction, you want to use that equation. So the final concentration is 0.05, the initial concentration is 0.1 is equal to K times 2.5 hours. And again, K is positive because it is a positive slope line. So you solve for it, you get 1.3. Now, the tricky part here is to recognize that K, in order to cancel everything out, the molarities are 1 over molarity over here, and hours is over here. So that means your unit is 1 over molarity hours, or second order reactions are going to be 1 over molarity times time, okay? So remember either one of those, okay? So part B may be a little more tricky to set up. What is the concentration, a final concentration after 5 hours? The final concentration is your X minus your initial concentration, which is 0.5. And this is where you use the K. And again, if you don't get the K right, as long as you show me how you'd set it up, I will follow through with your math. So 1.3 times 5. So X comes out to be about 0.12 molarity, 0.12 molarity. All right, so number 3, try this one. This one is a first order reaction, decomposes 99%, find the half-life. So this one you kind of have to do 2 steps in order to do that. So again, this is a first order reaction, so you want to use the equation for first order. So you're going to take final concentration, which is going to be 0.01 because it said 99% of it had decomposed. The original concentration is X, so it's going to take 0.01 X over X, and you end up the natural log of 0.01 is equal to the negative K times the time. So K comes out to be 0.025, 1 over minutes in order for that to work. And again, since it's a first order reaction, you just got to use 0.693, divide it by your K, and you get around 27.8 minutes. All right, so the last one I'm going to talk about on this particular video is this one. And this one, I'm going to show you a way to do these types of problems with pressure units. If you have a chemical reaction that is all gases, because gases, the pressure is related to its number of moles, you could do these types of calculations according to pressures instead of changing the pressure to moles and having to look at rates and convert things to molarities. It's going to save you a lot of time. So I have an initial concentration of my reactant. After 75 seconds, I have a total pressure of 150. After 150 seconds, I have a total pressure of 175. Calculate the rate of disappearance of N2O3. So I've already written some of this down, so you might want to pause the video here for a second. I just rewrote the equation just so I have something to write underneath it. So I have an initial concentration, initial pressure of 100 torrs. And so this is what we call a typical ice table. And we'll talk more about that in chapter 15. But what is the initial? I have none of the products here to start with. So something happens over time. So this goes down by a factor of X, this goes up by X, this goes up by X. And again, if I had a 2 in front of the N2, this would be a 2X, so on and so forth. But this side is positive, this side is negative, okay? So then at the final part, at this point in time, we're gonna say at 75 seconds, what exactly do I have in that container? So what I could do is, since I have the total pressure is equal to 150 torrs, I could put all of these equal to that 150. So I could take the 100 minus X plus X plus X is equal to 150. So one of the X's cancels, and so I have 100 plus X is equal to 150, so X must equal 50 torrs. Okay, so that means at that point in time, I have 50 torrs left of the N2O3. So I started a table over here just to kind of organize the information. So if you see it later, you kind of can see where I went with this. So after 75 seconds, okay, starting at 0, I had 100 torrs of my starting material, and my total pressure was due to just my reactant. But after 75 seconds, I started to make product. So I have 50 torrs, because again, 100 minus 50 gives me 50 torrs. And then my total pressure was given in the problem as 150. Okay. So then I have another time point at 150 seconds, and I have a total pressure of 175 torrs. All right. So at this time point, I have 50 torrs of the N2O3. I have a starting point of 50 for this one and 50 for the other product as well. So change happens. So this is a minus X, this is a plus X, this is a plus X. So this is 50 minus X, this is 50 plus X, this is 50 plus X. And we know the total pressure is equal to 175 after this time point. So that's 50 minus x plus 50 plus x plus 50 plus x. So two of the x's are canceled out. So I have 150 on this side plus x is equal to 175. So x must equal 25 torrs. So 50 minus 25 torrs gives me 25 torrs is going to be my N2O3. So, and you're going to see something here. There's a point to my madness of why I'm doing it this way. Okay. 75 seconds. Okay. I have a change of my initial torrs is, my final torrs is 50 minus 100. And that was 75 seconds. And this is going to be a negative. So this is my rate. So it's going from 50, it's going from 100 to 50, and it's over 75 seconds. It's 0.66 torrs per second. The time between 75 seconds and 150 seconds, okay, so another time frame, I'm looking at 25 torrs minus 50. Again, that's going to be a negative, and that's another 75 seconds. And I'll show you something here, and I could have done this much easier. 0.33 torrs per second. Okay, so the whole point of me doing it this way is I could then take these two numbers and take an average. So 0.66 plus 0.33 divided by 2 is 0.5 torrs per second. And that's the answer to the question. Now, could I have just taken 25, the final time point, minus the initial over the whole time? I would get exactly the same answer, okay? So the point of my madness is the beginning of our discussion of rates. We said at the beginning of the experiment, your rate is much faster than it is at the end of the experiment. So as you can see, the torrs are changing much more at the beginning than they are at the second 75-second interval, okay? So reason I do this, you could have just taken the 25 and gone all the way to this step to find your average rate, because again, that's all we're looking for is the average rate, okay? But I wanted to show you this so you could see that rate changes as the reaction progresses.